Today we continue the discussion of event modeling. So imagine an asset undergoes some process such as what controls with normal Brownian motion, and at the time of some announcement, such as earnings announcement or some major economic announcements such as FOMC rate decision, when the rate decision is released, an asset undergoes a sudden jump up or down. And after the jump, it continues to follow the clean process. So we want to understand how to model volatility and the dirty volatility and options under such dynamics. It's useful to consider two limits. In the first limit, the variance of the event, basically the return on the announcement squared, is much smaller than the total variance of the clean process, sigma squared t, where sigma is the clean volatility. However, if the variance of the jump on the event announcement is much larger or comparable to total variance of the clean process, explicit modeling by model jump is important. In this graph, you can see both density of the clean process, which is log normal, density of the distribution when the event variance is small, and the density by model distribution in the case when the jump is very large, and the corresponding probability density has two clearly defined bimodal peaks. So in this case, we choose the clean process to be log normal, so the clean volatility surface is flat, and the resulting dirty distribution has two peaks, and the implied volatility just has a hump in the center. But if the clean process corresponded to a volatility surface that has fat tails, the hump in the middle would still increase, and it would result in the typical W shapes that we see in the volatility curves corresponding to events. So now let's talk about how we can model dirty volatility surface if we know the clean distribution and we know the distribution of event. For simplicity, let's start with the Black-Scholes model for the clean process and the discrete up and down jump for the event. In this case, to calculate an option price under such a model, you can call the Black-Scholes formula two times with the spot shifted up and shifted down and taking the weighted average of the two, and that's going to produce you the option price for European options. For now, we're only considering European options. In this case, we can add any number of jumps and go from clean vol surface to dirty vol surface, or go from dirty vol surface to clean vol surface for any expiry, and this is a very well-defined procedure. As a matter of fact, we believe that this is exactly the model to create the W shapes that are observed in the market. There is one interesting detail here. It is important to point out that Black-Scholes event model is not a self-consistent model when the underlying process is not log normal, pretty much in all cases. We're using the same trick that we use when we trade from implied volatility surfaces, namely that we calibrate a different Black-Scholes model or a different Black-Scholes event model for each strike. So there is no one model here. There's an ensemble of different models that we calibrate for each individual strike. This is an engineering trick that allows us to parameterize prices as functions of strike. However, this is not a self-consistent model. You cannot write an SDE, you cannot write a Monte Carlo pricer under this model because there is no model. It's just an engineering trick to smooth prices across strikes. But now let's take a look at real-world examples when we start with an existing dirty vol surface, basically implied vols calculated from the option prices, and the dirty vol surface obviously has W shapes after the event. What this means that we calibrate jump probability, jump size, and jump width in general for up and down jumps in this case, and we extract this information from the market. Knowing the merchant parameters of the jump distribution, we can take the dirty volatility surface and reconstruct the clean volatility surface. Having the clean volatility surface, we can again add back the jumps on it and reconstruct the volatility surface from this model and compare this to the option prices or to the dirty volatility surface. When the parameters of the jumps are calibrated, you can choose for which expiry you want to match the shape. It could be one or more expiries that you want to use in your calibration. However, after you determined the parameters of the jumps on the event, and you calculate a clean volatility from the dirty volatility surface, you recover the term structure of all parameters for the clean process. In this sense, you have reduction of dimensionality. So usually your dirty vol surface requires more parameters than your clean vol surface. And you have only one set of the event parameters. So the total number of parameters described in the event distribution plus the parameters described in the clean vol surface is smaller than the number of parameters described in the dirty vol surface. When you have this machinery, you can implement several different workflows. First, you can start with a clean vol surface if you know how it looks like, if this is in the liquid name, and you mark your clean vol surface by hand by looking at vol curves prior to earnings announcements or right after the previous announcement. You know how the shape typically looks like. You can create a clean vol surface, add the events to it, and see how the dirty vol surface is going to look like if you want to create the dirty vol surface from scratch. Alternatively, you can start with the dirty vol surface observed in the market. You can extract from this event parameters, jump size, jump probability, and jump width, and calculate the clean vol surface. The clean vol surface may or may not be very smooth. You may regularize it, and then use the regularized clean vol surface to reconstruct the dirty vol surface, since you already have the jump parameters, and compare the resulting vol surface to the one observed in the market. That's one of the possible workflows. And as I mentioned, it looks like Black-Scholes event model that uses a separate log normal clean process for each strike. Seems to match the market pretty well for a large sample of names that we looked at. However, a consistent model doesn't seem to be calibrated as well as the inconsistent model. Either the consistent scale invariant model does not correctly describe the dynamics of the markets during the event announcements, or the market is using a simpler Black-Scholes event model description as an engineering approximation that that is not completely consistent, and there is a market opportunity. If you want to know more about what we do at Voladynamics, you can always email us at info@voladynamics.com. Happy trading.